Good morning again, and we learned how to relate deformations with forces or transverse displacement with the external loads that are given on a beam. And while relating that, we did a linear assumption that the system should be linear. So the assumption comes from small deformation and small slope, right? Change in slope is very small. So these two assumptions make sure that the beam's deformation is small within its linear zone. Okay. Now let me tell you at this point that even if the beam is elastically linear, beam can have large deformation called geometric large deformation. And we have shown the equations in the last class. What is geometric large deformation, right? In that case, you don't do that small assumptions. Theta is small, so tan theta is theta. You don't do that assumption, and that leads to geometrically large deformations. But still, the beam materially linear. Okay, so there are two things to understand. One is beam's behavior in a material direction, where I can have linear and nonlinear, and beam's behavior in the geometric direction, where I can have linear and nonlinear both. Okay, right. So with that linear assumption, we derived a fourth order differential equation, right? And we said that the force deformation relationships are linear. So if you increase the external load, deformation will similarly proportionally increase, but it is inversely proportional to the flexural rigidity of the beam. So if you increase the flexural rigidity of the beam, you will have lesser deformation. So increasing flexural rigidity means rigid beams. So if the beam is rigid, its deformation is going to come down. For example, for the same load, if you reduce the length of the beam, flexural rigidity increases, and that reduces its deformation. Okay, and we solved one or two small problems to get how to get hold of the equations that we developed, and we said that it's a four-order differential equation, and therefore it needs four boundary conditions. And these four boundary conditions can come from deformations, can come from slope, can come from moment, or can come from shear force, right? So all these can contribute to the boundary condition, but four boundary conditions are necessary. While doing one of the problem that we did in the last class, it was with a point load, and we said that the fourth order differential equation considers UDL. So how do you convert a point load to UDL? So we did a mathematical trick there, used rate delta function and converted it into a UDL form, right? And then you can do that integration and get the solution. There is other way is you can get the bending moment from the loads, and you can do a double integration of the bending moment to get deformation, right? So the relationship there is different. That relationship from bending moment, I wrote it in the last class also, is EI d square V by dx square is equal to M, right? So once you get that diagram, you can find V by just integration. So plus boundary conditions, you will need only two boundary conditions in this case. But in cases where a beam is subjected to many such loads, like many point loads and many moments, so this is not uncommon. This is very common. Okay. For example, if you have, I can just draw an example here. For example, if you have a floor, right? Let's say I have a floor, and the floor has beams running here. So there is one beam here, there is one beam here, and let's say there is another beam here, another beam here. So these are all beams. Okay. That's floor. Now you kept an almirah here, okay, in your house. You kept a table here in your house. Something here, maybe a lamp post. No, sorry, not lamp post. Maybe a lamp or something. Okay. Then if I bring out the beam will have a table. So there is a part of UDL here, and then there's a lamp. So this is a point load, right? And then this beam will give load to the other beam. So there will be a load from that beam coming here, support structures, then support structure here, right? So a beam, if you see, will have so many point loads acting on it with distributed load. So it's not very uncommon to have this sort of this sort of loading on a beam. Okay. Now, when you have something like this, what are we going to do? You can obviously draw a bending moment diagram, something like this, maybe, and then this, some bending moment diagram you can draw, and you can do double integration on the bending moment diagram to find your deflection. But if you want to use the fourth order deflection equation, how are we going to use it? One thing is you can divide your section into various small section. One section is here, the next section is here, the next section is here, and then so I can divide it into 4 sections, and I can do integration of the 4 sections separately. Now, while doing that, even in doing the bending moment thing, at every section that you get, you have to have 2 more boundary conditions, right? You have to make sure that the boundary conditions at this point matches whatever you get from there and whatever you get from here, this side. This is called continuity. So the deformation and the slope has to be continuous, right? So that continuity has to be maintained, and that continuity equations have to be solved. So how many you are going to get? 2 deformation and slope, another 2 here, another 2. So many equations will come up to be satisfied the constant equation, and that is not an easy job to do. So is there a better method to solve it? Let's look at if there is a better method to do it. So one of the better method is called using singularity functions or discontinuous functions. That's the name they give, or they're called Macaulay bracket. Okay, it's a very easy method. You can use it very easily, just very straightforward and very easy to code in computers. This is what I just discussed. The same thing is written here. In this case, you have beam with the UDL, right? And it can follow the fourth order differential equation and you can solve it. But when you have a point load, it's difficult for you to solve. So you probably need to divide the zone into 3 zones. One part is here, 2 part is here, and third part is here, and solve them separately. Finally, you connect them, right? When you connect, you make sure that the deformation and slope at this point are same, deformation and slope at this point are same, right? So this is what is written here. So your V of X, so you get shear force from this. The shear force become P plus WL by 2 at this location, WL by 2 at this location, and WL minus WX. So this formula for this location. Right? So you see there are 3 different domains, and you can do these integrations at 3 different parts. Right? Similarly for moment also. So you need 6 boundary conditions extra. 6 constant conditions will come extra to solve this, which is not easy if you do it by hand. So there is a better method. What is this better method? Called Macaulay's functions or Macaulay's bracket. It's very straightforward. So just pay attention and it will be okay for you. It says if you have a function f of x, you can write that function as, okay, as this bracket, bracket within bracket x minus a power n. Let's say a function. That function is equal to, how do you read that function? That function is mathematically equal to x minus a whole n. Okay, normal when x is greater than equal to a, and it's 0 when it is less than say. So this is a nice way of representing a discontinuous function. If there is a discontinuity before the point where it's 0, and after the point whatever value it takes. So for example, if you have something like this, a step function, if you have something like this, let's say this is a, right? So before a, the function is 0, and after a, the function is constant. Okay, so I can write that as x minus a power 0 within bracket. So there is bracket x minus a power 0, which means that it is 1. So let's say this is 1, which means that 1 when n is greater than 0 and x is greater than a. N is not necessary here, n is 0 here, and is 0 when n is greater than 0 and x is less than a. Okay. For here, n is not necessary because n is already 0, so that means it is 1. Okay, Now, there is another representation of this. If I do an integration of this, because in differentiation, in deformation calculation, we have to do integration of this function. So if I do integration of that function here, minus infinity to x, what do I get is, for n integer, x minus a minus 1 for n equal to minus 2, x minus a 0 for n equal to minus 1, and x minus a n plus 1 by n plus 1 for n greater than equal to 0 for any value. Why did I give minus 2, minus 1 here? The minus 2, minus 1 are here because the maximum power, negative power that we're going to get in this kind of problems, in our deformation problem, is minus 2. That's why minus 2 is explicitly given. Otherwise, the formula is like this when it is greater than n, and like this when it is less than 0, okay? But integer. So this n plus 1 is here and n plus 1 is not here. So this is a regular integration formula. This is not. That's because of the discontinuity. We'll come when we go to a physical problem. We'll say you why is this, okay? So here is another problem that you have, a small example problem. So this is a function f1 of x which goes to a as a 0 and then it goes linearly, right? So here the function is x minus a. This function is x minus a, and this function is 0. So how do I write it? I write it as x minus a power 1. Okay, which tells me before a it is 0, after a it is x minus a. Okay, so these two functions which are written as the two functions can be written as a single function. This is how you represent a discontinuous function. So it can be useful for our beams cases. We will see that. Before that, just go through this problem, because this 1 minute. Yeah, before this, just go through this problem. This problem is going to help you to understand a few how to write this, how to read or write these functions. Here is one of them, which says y equal to 3 into x minus 2 power 0. Okay. All right. This, let me not write it here. Same thing written here, right? So y equal to 3 into. Now 3 means the value of magnitude is 3. X minus 2 power 0. What is x minus 2 power 0 going to be? So if I write it, so I have a division at 2, right? So since x minus 2, so this is my division 2. Before 2, what is going to be? Y is equal to 0 for x less than 2, right? And what is going to be after that? So y is equal to 3 into something power 0 is 1, right? 1 for x greater than equal to 2. So it is going to be 3. So you're going to have a function which is like this, then this. Okay? Clear? Now look at the next one, this bottom one. How to write this? Okay, so I'll rub it again. Okay. The function, it says that y is minus of 1 by 4 x plus 1 whole square. So now x plus 1 bracket can be written as okay. So therefore, the discontinuity starts at minus 1, right? So y is equal to 0 for x less than minus 1. So for minus 1, this is my zone for minus 1, this is 0 here. And more than that, greater than x greater than 1, what we are going to get? Y is equal to minus 1 by 4. This is x minus 1. So this bracket will convert to a first bracket or circular brackets, x minus 1 whole square, right? So it's going to be minus 1 by 4 x plus 1 whole square. So now it is a parabola, so it's going to go like this. Okay, clear? Now look at this one. You try it yourself. This one. There is a mistake here. I suppose that should be 1. Yeah. Yes. So can you do this? Can you check this whether this is correct or not? How to draw this? So you see this function. See this function and draw accordingly. Any question here? Have you written down the function? Y is equal to 2 into maculus bracket x plus 2, 0 minus x power 1 in maculus bracket plus maculus brackets x minus 3 power 1. Okay,
sir,
now try it yourself.
Point...
Yes, Kanika.
Sir, I have a small doubt, sir. It's in the first slide, sir. Slide number 6, I guess. Slide number 6, sir.
Yes.
The previously. Yes.
Yeah,
Sir, in this actually we
6.
wrote this. Sir, we wrote when n is greater than 0 and x is greater than a, we wrote to be 1. Like we wrote to be equal to 1 and almost, sir. Is that this macros function bracket power 0 or power n, sir?
This is power 0. So this, for this case, it is not, this point is not valid at all. It is not necessary here. You have already given a value to be 0. This is what you do in maculus bracket. For n equal to any integer, for greater than a, it will be these brackets. So this maculus bracket will convert to normal, circular brackets. And less than a, before the discontinuity starts, it's 0. But remember, always you have to go only in one direction. You cannot.
Sir, I'm
go.
sorry, sir. I have network issues. Sorry, sir. Like, so you were saying?
Yeah, I was saying that. Look at this function only. Okay, your maculus bracket of x minus a power n is equal to x minus a power n when x is greater than a and equal to 0 when x is less than a. So when it is discontinuous, before the discontinuity it is 0, and after discontinuity it gets into a real function, whatever it is, x minus a power n or x minus a power n by not 2, 3, 4, whatever it comes. Right? Okay. So we will do some problems. No, it will be easy for you to understand when we'll do some problems. Yeah.
Sir, 1 minute. I just wanted to know if that's
yes,
x minus a the whole power 0 or n. Sir, that's also like in that is equal to 1 and 0.
0. This is
okay,
0.
Sir. Because if that is 0, then we don't need the condition for n also. Because n is 0.
Yeah, that's what I wrote. No, I cut it out. You do.
Okay, sir.
We don't need this condition for it. Yeah. Okay. Now, please do this and let me know whether you get the same function as this one. And this probably not that. Okay. So there are, how many discontinuities are there? One is at -2. One it has 0, right? X minus 0 here at 0, and the other one is at +3. So there will be a discontinuity here, there will be a discontinuity here, and there will be a discontinuity here. Okay. The function will change at those 3 locations. Now, having said all those things, how do you convert? Which graph is wrong? Which graph is wrong? Kanik, that's what you were writing, right?
This last one, sir. The 3 functions.
This one?
Yes, sir.
What is wrong there?
I think it should be at 1, sir, not 2. I mean, like on the y-axis, it should be at 1.
Which one should be at 1?
Oh, sorry, sir. Sorry, sir. I didn't see it.
This line?
I didn't see it 2 multiplied, sir. Sorry, sir.
And there is a 2 here, yeah. Right. So how do you convert then? We have learned the function, but now we need to know how I convert my physical loads into those functions. Right. We have to understand and know that. So this is where the singularity things come in. Look at this beam. So you have a beam, and then you have a point load at A. P point load at A. Right. This can be represented as the same beam, okay, and then there is a slightly distributed load here with epsilon is the area over which or the length over which it is distributed. Okay, then the intensity of distribution will be P by epsilon, right? Intensity will be, this is my epsilon, this area is epsilon, so this length is epsilon, so the intensity of distribution is going to be P by epsilon. Now this can be written in my fourth order equation because W is now a distributed. So I can write EI d4V by dx4 is equal to W minus. I can write it. Now because there is this epsilon which is going towards 0, right? In an actual case, epsilon tends to 0. It's the limit epsilon tends to 0, W becomes equal to P. It has a singularity of -1. So we write it as W is equal to P is the intensity, X minus A is the location where the load is acting, with the Macaulay bracket and power as -1. Okay, we write it like this. Now it is equal to 0 for X not equal to A, and it is equal to P for X equal to A. Okay. All right. Now let's look at bending moment. How do you convert a point moment if it is there? So this point moment, let's look at this. There is a beam here, and there is a point moment that is acting M0. This point moment can be converted into two forces. One is acting upward P, and one is acting downward P, right? And they are epsilon distant apart. So the moment arm will be epsilon. So P is equal to M0 by epsilon, right? And then again, I have to convert to UDL. So from P to UDL, we know how to convert. So that becomes W is equal to P by epsilon, which comes from here. That is equal to then P is equal to M0 by epsilon. So it becomes M0 by epsilon square. So epsilon going to 0 two times here. One is because of the P, one is because of the arm length, right? So therefore, I'm giving here as -2. Okay, there is a -2 here. All right, the physical understanding of this will come a little bit later. Once I solve a problem, I'll tell you why we are giving this -2 here, why we are giving this -1 in the force case. So this is equal to 0 for wherever X is not there, equal to A, and it is equal to M0 wherever X is equal to A. So that's how you write these two functions, right? It's very easy to write this function. Discontinuous functions of various loads. So here is a chart that tells you if you have a discontinuous function, what are the things that you can use. So when you have a moment discontinuity here, so there is a moment that is acting here. Okay. So sorry. And distributed load, we write it as a -2. For a shear force, there will be an integration, so it becomes -1. And for moment, it becomes 0. Okay, because you are integrating, right? So once you integrate, it becomes -1, and then once you integrate, it becomes 0. Similarly, for a point load, you have -1 in the distributed load, and then there's after integration in the shear force, it becomes 0, and in moment, it becomes power 1. Okay. Similarly, you have the other two loads. Now I will tell you why do you need to do that. Suppose I have a beam. And there is a point load here, P1. And there is another point load here, P2. Okay. And let's say my X starts from here. And I'm doing my calculations from this side. And let's say this distance is A, and this distance is B. Okay. Now, when I let's say I'm trying to draw my shear force diagram, and I'm walking from this side. Right. So what will be the effect of this P1 here? There is no effect, right? In my shear force diagram, there won't be any effect of this P1 till I reach A. Once I reach A, the shear force diagram will come down because of the load P1. And then it will continue. The effect of P1 is still there, but effect of P2 is not there. And once you come to B, your effect of P2 will start, right? And it will come down again and then go like this till the end. Is it true? So if I draw shear force, so there will be something called, P1 plus P2 by 2 here, or some relationship will come. So this may be RA, we can write it as RA. It will go like this. Then at this point, it will come down, right? This is the effect of P, and the effect of P will continue. Effect of P will continue till here, and then the effect of P2 will come. And then it will go this. This is RB, right? And that's your P2, that's a P1. Is that correct? So if I see I don't have any effect till this point of P1, effect of P1 started from here and it continued till the end, right? And effect of P2 started from B and continued till the end. Okay, clear? Now this can be written in that function form. The functional form is this. Now if you integrate this function, what happens? If I integrate that function, this is the UDL. If I integrate that function, it becomes P bracket x minus a 0, right? P bracket x minus a power 0. Now when I write that P into x minus a power 0, that means before x equal to a, it is 0. And after x equal to a, it has its constant value. So this is the constant effect of P1. Similarly, this is the constant effect of P2. That's why you gave -1 there, which makes sure that once you integrate it by one time, you get a constant effect of that P1 and P2. Similarly, if you have a moment, okay, if you have a moment, you have to do twice, because the effect of moment will come only when you have bending moment into it. And to get bending moment from deformation, you need to integrate twice, not once. Okay. So let's get into one example. There is a few things written, whatever I've discussed, it's written here, and this is the way you have to solve the problems. First thing is always you have to convert your discontinuous load into a single equation. Okay. Let's look at this problem that we have here.
Sir?
This problem that we have here is, yes.
So small doubt, sir. Actually, when we integrated p into x minus a power -1, we got p into x minus a power 0 now, sir. Sir.
Right.
So that does not follow.
Yes.
It's not necessary to follow any rules of polynomials, because when we integrate 1 by x minus a, it becomes ln. So because here also it's a polynomial. So
I'll tell you what to do. We'll solve one problem, that then your problems will be solved. When do you get polynomial integrations to be done, and when you not do it? Okay. I'll show you with the examples here. Right. So now this is a simply supported beam I have, and that simply supported beam has a point load here P and a point moment here M. Okay. Now what we have to do is I have to convert that first into a distributed load format of a distributed. I can do it in two ways. One is I can write this load itself without the boundary conditions or the boundary forces. Other way is I can add the boundary forces into it. What is the difference between them? When I don't add the boundary forces, that means I write Q directly as this without adding RA and RB. I do not put the boundary conditions. I have to put the boundary conditions while doing the integration. So there will be integration constant that will come, and I have to put the boundary conditions there. The other one is when I use the boundary conditions into it. So that means RA is calculated, RB is calculated, and they have been put in the QX itself. In that case, I have already used my boundary conditions, two force boundary conditions, and I will not use those two force boundary conditions in my integration. I'll use only deformation boundary condition integration. So therefore, my requirement of boundary condition will reduce from 4 to 2. Okay. The advantage of doing that is you do not solve all the force C1, C2, C3, C4 together. You just solve only two of them, and rest of the two of them are found from the forces already. Okay. So if I don't use my free body diagram, the QX is going to be P. This is acting at L by 3. So P into X minus L by 3. Since this is point load, I write it as -1 here. And since there is a moment acting as 2L by 3, I write x minus 2L by 3 minus 2. Okay. And this is valid from 0 to x between 0 and L. Right. Now, if I use the free body diagram, I will have a RA here and I'll have a RB here, and you can calculate RA, RB. These are calculated here and you can see the values here. Okay, they are calculated here and you can find the values. You can do it yourself also. So once you know RA and RB, how do I write it? Remember, my downward force was positive, right? And my anti-clockwise moment was positive. Therefore, my upward force is going to be negative. So it is minus RA into X. Power is minus 1. Okay. Plus, same thing comes P into X minus L by 3 minus 1, M0 minus 2, and RB into X minus L inverse. Okay. Power minus 1. So this is my Q of X if I use free body diagram. And this is useful to use it because in that case, you don't have to put two boundary conditions because RA and RB are already understood and known from using those boundary conditions. Okay, now these are my formulas to integrate. Formula is when n is less than 0, I don't have a denominator here. When n is greater than 0, I have a regular integral formula, regular integration formula where we have a denominator n plus 1, regular polynomial integration. This is my equation, EI fourth derivative of V is equal to minus Q. This is my fourth order differential equation for deformations. And that is going to be equal to, what is my Q? Minus Q now is going to be minus of this, right? The whole thing. So you put it RA of this, and this. This is no more necessary because I'm walking from this side. So anything that is beyond this is not necessary. So RB, the effect of RB will be only after this, not before this, right? So RB, whether it's there in the equation or not, doesn't matter to us because we are not looking anything beyond L, right? So that way RB is not necessary. So,
మామూలుగా చికెన్ అడుగుతున్నాను.
so that's my equation. Excuse me, Satvika, I'll just mute you, okay? Right. So what do you get now? Just simple rule of integrations are to just follow this formulation. So if I integrate one time this one, I get third order derivative, and that is my shear force. And this becomes minus 1 becomes 0. So its effect starts from there. If you see shear force, RA effects will start from there. This also becomes 0, but its effect will start from L by 3. This is minus 2, and its effect will start from 2L by 3. This is not necessary. All are minus 1 here. See, there is no denominator that has come here. Okay. Next, if you integrate once more, you get moment where this becomes RAX. Remember that whenever there is a support motion, the moment because of that is RA into X. So that's what's already come. And you see, I've taken the bracket out now because this 0 power is gone. Okay, it has become 1 power now. P into X minus L by 3, still the bracket is there because it starts from L by 3, right? And this starts at 0. Minus M0 X into, see, this has become 0. So its effect in the moment is just a discontinuous jump, sudden jump. So 0 means there is a sudden jump. Okay, and then if you go for slope, you have to integrate once more. So RA X square by 2, see the denominator here has come already by 2, and that has come because now the power is positive here, that is 1. Okay, when the power is more than greater than 0, I use the denominator. So it becomes a regular polynomial integration. Minus P by 2 here also by 2 because this is also positive, minus 1 was there. But here nothing has come because it was 0. Okay. Plus C1. Now I did not use any C1, C2 here because they have already been used in solving my boundary conditions, boundary forces. So here in the slope, I have to use because I have not used slope boundary condition yet. So there will be C1 here. And again, if you integrate, you get C2 constant, right? So this becomes X cubed by 6 because 1 other 3 will come, 1 by 3 will come here. And this also by 6, this is by 2. Now you get this, right? So this is your solution for deformation of the, you have to find C1 and C2. How do you find C1 and C2? We know the boundary conditions. The boundary conditions are V of 0 is 0. This is a simple supported beam, and V of L is also 0. Now V of 0 means none of these are available, right? Only C2 is there. This is not valid at x equal to 0 because it's valid after L by 3. This is not valid at x equal to 0 because it is valid after 2L by 3. So these two are not there. This becomes 0 because the x equal to 0 means RA is 0, right? So you have only C2, and therefore C2 is going to be equal to 0. To find to use the boundary condition at L, I have to use. So in that case, this will be active. L is greater than L by 3, so that will be active. L is greater than 2L by 3, this is also will be active, and this will be C1 by L, right? C1. So that gives you your C1 to be this value. This is what has been done here. Okay. So now you know C1, C2. Once you know them, you know your slope and your deformation. Both are now known. And then you have to draw the function. Okay. How do you draw it? You have to draw. Now, while drawing it, this is the case you have to do. Between 0 to L by 3, there is one boundary condition at L by 3, one discontinuity. There is one discontinuity at L by 3. There is another discontinuity at 2L by 3, right? So these two are discontinuous. So 0 to L by 3, this is your value of phi of x. L by 3 to 2L by 3, the value of L, this is it. So from 0 to L, this is your, this one and this one is your active part from 0 to L by 3. This will not be there and this will not be there. After L by 3, this will be there along with these two, but this will not be there. And after 2L by 3, all of them will be there. Okay. So that is what is written here. And once you write them, you can draw the deformation diagram.